Well, I'd like to welcome you to this afternoon's Jones seminar. It's me again, Keith Paulson. I don't normally do this, but Brian Pogue is away again, so he asked me to do it, and it's a real pleasure because I know today's speaker as well from Dartmouth, Saeed Hassanpour. And you probably read about Saeed. He's an associate professor now in the Department of Biomedical Sciences, data science, computer science, and epidemiology here at the Geisel School of Medicine. And I first met Sohail a couple of years ago, and he's probably not going to talk about it today, but if you're interested, he does a lot of natural language processing as well, which is really cool. He's going to talk to you today about his work using artificial intelligence, or deep learning, however you want to call it, in pathology. And it's a really ripe area. Of course, he's going to replace pathologists. I don't think we have any pathologists here today, which is good because he's going to sort of replace them, I assume. One thing you don't, as you know, I like to always tell you a few things about the speaker that you don't read about on the paper. One is Saeed just recently won a very prestigious university award from Agilent, which is, you probably know Agilent. It used to be HB, but now Agilent for many years, I guess. Which is, there's one given per year, so he competed nationally amongst many highly qualified applicants to win that, so that's a very good thing. The other thing is, if you kind of look at Saeed, one thing I know, he's in the gym often at about 5:45 a.m. lifting some heavy weights, because I've kind of followed him, and he's a lot stronger than I am, probably, certainly physically and probably mentally as well, so Saeed, welcome here, and we'll look forward to hearing from you.
Thank you very much, Keith, for the high introduction. Thank you very much, everyone, for coming today, and thank you, Keith and Brian, for inviting me. I'm actually taught a course with George, Professor Sybenko, a couple of years ago on applied machine learning here in the engineering school at FAIR. So I'm really excited to be back to talk to faculty and students, and I'm really looking forward to the discussion and potential collaborations that this talk might actually result in. So I'm going to talk about the application of artificial intelligence in pathology informatics today. And I'm going to start with actually basically a high overview of artificial intelligence in general. As you may know from popular media, or if you have read any papers, in data science or engineering, there has been a tremendous amount of progress in the last decade in artificial intelligence. And this actually progress has provided new opportunities in different domains for AI applications that I'm going to talk about actually is potential basically applications in the biomedicine and more specifically in pathology. So here, very actually high level overview. As you know, machine learning is a subset or a branch of AI and artificial intelligence. And most of the actually progress that we see these days in AI and machine learning is coming from a subset of this machine learning methodology, which is commonly known as deep learning or deep neural networks. So I know George is teaching this class right now, actually in the fall quarter, and a big proportion of class is actually is focused on covering neural networks. So by no means I'm going to actually go in details and talk about these in detail. But basically, the methodology that rely on these techniques have shown good actually performance in comparison to human counterparts, and in some tasks actually they even exceeded human performance. So in our lab, as Keith mentioned, we actually work on many different modalities, many different type of data. We actually focus on the application of these deep learning models and machine learning methods to analyze mostly unstructured data. So these are images or text to help the data scientists to understand their data better, and also help clinicians in medical practice. So here you can see actually a few directions that actually in my lab. We actually, as we will talk more later today, we actually work on analyzing medical images in the domain of pathology, radiology, and also more recently dermatology. There are lots of actually imaging focused subspecialties in this in medicine that all benefit from these methods. We also, as Keith mentioned, we actually work on NLP and natural language processing to extract information from electronic medical records and clinical notes. And our overarching goal is combining these medical features, features that are coming from medical images, and also clinical information coming from the text, and also other structured data, and also potentially genetic data to build comprehensive risk assessment for different conditions and help with the diagnosis and predicting prognosis for patients. But as I mentioned today, specifically, I'm going to talk about the application of AI in pathology informatics and pathology image analysis. So histopathological characterization of microscopy slides is an important task in pathology. So it is actually is used for the diagnosis, for predicting that what's going to happen for the patient in the term of the progress of the condition, and also the guided treatment. And I should say that this actually task is done very routinely, and there's a lot of actually microscopy images are generated every day that we don't have enough pathologists and workforce to actually read these images. And both in the US and particularly in the developing countries, actually we're facing shortage of pathologists that actually to basically in medical practice. And even in a hypothetical actually case that we had enough pathologists in clinical practice, this task is very laborious and is very complex and difficult. So we actually in different tasks, we actually have been studies that show that there's a lot of variability between pathologists in reading slides, and actually reduced accuracy can really in reading slides can really hurt the patient's outcomes. So I actually want to acknowledge the other basically work that has been done in this domain. This is the very, as you may know, it's a very hot topic. There are actually lots of academic groups that work in this domain, and we also seen actual rise of startups and lots of actually big companies like Google and Google Health and DeepMind that actually specifically working on histopathological analysis of slides. So today I actually going to first talk about a few applications of this technology in various domains, particularly colorectal polyps, celiac disease, and lung cancer. And then I'm going to switch and talk about some more novel methodologies, because I know you guys are engineers, I'm an engineer too, and we enjoy actually building new methods and solving new problems. So I'm very excited to share some of the actually methodologies that actually it just got published, and I've not shared them before. So this is the actually exciting part of this talk. I hope you stay till the end so we can cover it. So first, let's start with some applications and why AI can be useful in this domain. And and I want to just first actually give you a little bit of background about colorectal cancer and colorectal polyps, and then I talk about the application of AI in this domain. So colorectal cancer is the second deadliest type of cancer in the United States. However, there is actually a great opportunity to actually prevent cancer, because these colorectal cancer, majority of colorectal cancer cases, they're raised from these growths in the lining of colon and rectum that are called colorectal polyps. So if a patient goes through colorectal cancer screening, colonoscopy, and these polyps are actually detected and removed, the progress of cancer can be stopped. But one major actually issue with these polyps is they reoccur. So the patient needs to actually frequently come back for actually active surveillance. So one factor that actually affects the management of the patient and the frequency of subsequent colonoscopy is the histopathological characterization and classification of these polyps. But it turned out this classification of polyps on microscopy images on histology slides is a challenging task. So I went to PubMed and Google Scholar and looked for the studies that actually studied this challenge, and I found actually several studies in the last 25 years that actually task more than, like, multiple pathologists. Some of them are general pathologists, some of them GI pathologists, to actually read these slides and they compare their agreements and variability in their basically classification. So here you can see the number of polyps that actually they look at, and this is the reviewer protocol. And here you can see the kappa coefficient, which is the measure of agreement between these pathologists, and you can see in almost all the cases the agreement between the pathologists, even GI pathologists, is in a fair or moderate domain. So this actually can subsequently really affect the frequency of the patient coming back for colonoscopy. Like, there are two cases, like hyperplastic and sessile serrated polyps, that are actually commonly are mistaken for each other. If you have sessile serrated or polyp or SSP, you have to come back in 3 years. And if you have HP polyp, you're fine. You can come back in 10 years, but you can imagine if somebody actually mistake SSP for HP polyp, that might be actually very bad consequence for the patient. So as you can imagine, it's a very important task. So to solve this problem, we decided to build a deep learning model to help with this classification on histology slides. And this is the collaboration between me and my group and Dr. Arif Surwanata. Actually, he's here with us in the audience. Thank you, Arif, for taking time and coming during your busy clinical service. So we actually talked about how we can actually solve this problem, and this is actually a collaboration that started back in 2016 to build this model. And other pathologists in Arif's group actually help us as well. So we actually decided to collect a data set, and this data set is composed of around 700 histology slides. So these are H&E stained histology slides. These are basically routinely used by pathologists to do this characterization for the subsequent management of patients. We, as you may know, is common in machine learning. We used some portion of this data set, in this case 2/3 of the data set for training and for hyperparameter tuning, and the rest for testing the data. A little bit about the actually type of polyps that we focused on. These are actually 5 different types. Hyperplastic, you can actually see the list. I'm not going to read that. And these are actually our classic examples of these polyps. So we actually look for the polyps that actually they are classic, they are the representative of their class, and they can be, as much as possible different from other classes. So you can see the different examples of histology pattern for each class, and these are actually the focus of the standard guideline for colorectal cancer screening in this domain, and most common type of polyps among patients. So our deep learning model in this actually project is supervised, so we needed label data, so we asked 2 pathologists to annotate these slides, so basically classify the histology slides and assign the basically class from one of these 5 different type of polyps, and also normal. We actually anticipated that some of these slides can be normal as well, so we added one additional class of normal in to our model. And we actually, whenever that, so 2 pathologists, they independently annotated them, they classified them, and whenever that they actually disagreed, we asked actually Arif as our senior pathologist to actually resolve the disagreements and have a discussion. We had a discussion with our group of pathologists, annotators as well, to actually see their points and have a basically gold standard based on discussion and the expert opinion of Arif. And And also, I should point out, this is the important actually factor in building this model. These histology slides actually are very large, commonly tens of thousand by tens of thousand pixels. So these are they are like several gigabytes, and they are very, actually challenged to analyze and even loaded on the GPU or in memory. So we actually asked our pathologists to annotate the polyp on the slide, because the polyp is very large. It's a very high resolution, basically, image, and only a small part of these like tissue is actually correspond to polyp, and most of it is actually normal tissue. So we asked our pathologist not only classify the whole slide, also put a bounding box and an outline around the polyp and outline the regions of interest for each polyp. So these are these outlines or crops, image crops as we call it. And we actually collected like these cropped images for every type of polyp. And you can see they are like kind of balanced among these different types. So to build this model, we adopted a sliding window strategy, as you might, as you might imagine. We actually we focused on a small part of the image each type. We actually passed it through a deep neural network. In this case, is a resonant residual neural network for those people that actually have taken deep learning class or taking machine learning class with George this quarter. You probably familiar with this architecture. I'm not going to in detail about it because I don't have time. But this is the common network architectures in deep learning, and we did that for actually all the different basically windows. So it's a sliding window strategy. And at the end, we actually develop a heuristic or a rule based on consulting with Arif, our domain, and the other domain expert pathologists to actually aggregate the results from each slide. So we actually put the minimum amount of actually windows that should be like with a high confidence be classified from a certain type of polyp to actually classify the whole slide with that type. So here you can see the evaluation result of our model on 239 test sets. So these are actually, as you can see, our total accuracy is 93%, and actually you can see the 95% confidence interval. We also reported precision recall from score in total and also per each class. And these are, if you actually remember our kappa coefficient from the previous, previous slide. So these are very promising, and we actually, I think I put the footnote in a couple of slides before. We published this result in 2017 in the Pathology Informatics journal. So this is all good, but this was a preliminary study, and it has some shortcomings and limitations. So first of all of our data is coming from one institution, our hospital at DHMC. So there is no actual evidence here that our model can do as well on actually data is coming from other hospitals, because other hospitals might have different scanners, different protocol for staining, and even the ethnicity of the patients that actually at their cohort actually might be a factor in the performance of our model. And also, as you see, we didn't compare our performance to actually any other practicing pathologist. So with the support from COBRI, actually from epidemiology department, we actually continue this research by collecting data from actually different institutions. So we were lucky enough to have access to 513 slides of polyps from vitamin D and calcium polyp prevention study. This is actually a very elaborate clinical trial that actually has been run for 20 years. And these 513 digitized slides are coming from 23 institutes across 13 states. So it's a very diverse actually data set. And in this actually study, we actually asked 5 DHMC GI pathologists to actually annotate that. And we actually we basically establish a gold standard on the actually majority diagnosis and classification of these 5 pathologies to actually to really polish and establish a gold standard to make sure that what we actually consider as the class, as a gold standard class of a slide is really truly reflective of the actually polyp in the slide. So what we did, we replicated the study with around 400 whole slide images coming from actually DHMC. We use this for internal, this internal data set for the development, and also for internal, some portion of it was used for internal evaluation. And also we used a whole 513 whole slide images coming from 23 external institutes for external validation. So I should mention that we actually, this study was much newer. We actually decided, we actually find out one of the original polyp classes, traditional searched polyps, that are actually very uncommon in the external data set. There were only 12 slides from that. So we decided, because we could not basically have enough statistical power, we actually decided to keep only 4 of the actually polyp classes and basically run an evaluation on those. And here you can see that basically the distribution of the polyps and an internal test set and an external test set, and also number of patches that actually we extracted on these 2 different data sets and their size. So this is basically the summary of our evaluation on the internal test set and also external test set. The interesting thing that you can see, actually we could replicate our result on our internal test set. I think it was 93% overall accuracy, and we got a little bit higher, 93.5% accuracy in our internal data set. And what actually is very exciting here, we actually went back to the pathology report and we got the actually basically the diagnosis, the classification of the pathologist at the point of care for all of these slides, and compare that to our model. So this is our local pathologist classification for these slides, 91%, and we could actually outperform that, 93%. However, this is not, I want to say, although that actually is a little bit higher, it's not statistically significant. However, in our external test set, you can see the local pathologist accuracy was actually around 91%, and our actually accuracy was around 86%. And it turned out this actually difference is significant. So we are very excited actually that we could not only show that we can get a good result, we can actually potentially be on par with what pathologists are actually classifying on these, like at the point of care. So we actually, in our this is actually the result of this. I think I have in a footnote. Right now is under review in a clinical journal, and we're hoping to publish that soon. But these are some more basically evaluation, basically image and figures from our paper. As you can see, we actually have the performance actually of the GI pathologist, and in our actually study, those are the people that we use for establishing the gold standard, and the local pathologist, and actually the ROC curve for our model, and we compare that for each type of polyp. As you can see, we actually, this cystal-searched polyps are a very tricky case. They're commonly actually mistaken with HB. And we saw that we actually have a little bit lower performance that we hope for. And actually, at the end of this talk, I'm going to talk about like new methodology that we developed to actually enhance, to close the gap. It's a small gap even for this tricky class. So now I want to switch gears a little bit and talk about network visualization. So as you may know, one of the very general criticisms that deep learning and machine learning models receive is they are black box, and it's hard for the human being, and particularly in the medical domain, for clinicians and doctors get insight in these models and actually verify the results. So here we actually use a network visualization methodology to actually highlight the part of the whole slide images that contribute the most to the classification result of our model. And by highlighting that, we provided them this opportunity to pathologists to review them and confirm that. So our actually methodology is based on the guided backpropagation that actually is widely known in network visualization domain, and we actually published this result in the Computer Science Conference a couple of years ago as well. Here is one actually demo sample that actually showing from our basically data set. So here you can see the original images. This is actually how pathologists actually annotated the polyp in the whole slide. This is actually heat map of the probability of the polyps in these histology images based on our sliding window strategy. And we actually come up with some sort of segmentation based on this heat map to actually outline the polyps. And we actually verified by a group of pathologists that qualitatively verified that actually these visualization are actually on target for the polyps. So as a result, our model actually looking at the relevant part of the slide for making these classification decisions. So I want to quickly talk about the next slides, next steps for this project. So we're currently in the process of building application that actually can be used by pathologists in clinical practice, and we are interested to actually run a clinical trial to actually compare the use of this model to what actually has been done right now without actually use of AI, and show that the use of this model in clinical setting can actually improve accuracy and also helps with the efficiency and reduce the time that the pathologists use in reading the slides. Also, as I mentioned, we are actually, interested in developing new methodology to even to improve our results even more. And this second bullet actually is the focus of NIH R1 grant that we recently received that is focused on extracting these medical imaging features and combining that with the information that we are extracting from electronic medical records for comprehensive risk assessment of colorectal cancer and reoccurrence of these polyps. So we are actually interested in combining these medical image analysis models with actually NLP methods for risk prediction. And we are actually interested to expanding these methodology to other applications and different types of cancer and lesions. And I'm going to talk a little bit about that in the next few slides. So, is there any questions so far? Or I switch and talk about another application? So please stop me if any part is unclear or you have any question. So very quickly, I want to talk about two other applications before I talk about our new methodologies. So when we did this, I talked to our pathologist collaborators, and I told them, well, this is great, but what's the most challenging type of classification in your, in your practice? And several pathologists point out to me that actually classification of lung adenocarcinoma, lung cancer, is very challenging. This is mostly because of the heterogeneous nature of lung adenocarcinoma and actually subjective criteria. Also, this actually lung cancer is usually mixed histology, so you have actually multi-class classification. You usually have actually more than one classes and more than one type of feature present in a slide. And it's a very important task. Actually, this determines like what kind of treatment the patient is going to get. And so because we are feeling very confident about our methodology, we decided to actually to work in this domain and see how these methods are actually going to work in these more challenging problems. So here you can see basically the classes of lung cancer histology that are the most common, and we focused on lipidic, SNR, micropapillary, papillary, and solid. So I know that, and there are some samples. I know that this might be a little bit, too clinical, but micropapillary and solid are really actually important type, and are usually associated with the the worst prognosis. So even very small part of actually a slide, it has these micropapillary or solid features. It's very important for a pathologist to actually not miss them and actually recognize that and incorporate that in the prognosis and treatment of the patient. So our data set is composed of around 400 actually whole slides, and you can see the distribution of whole slides across different classes. Also, we have normal tissue as well, or benign, that we actually used as a background class. And you can see that actually as I described in our sliding window methodology, we actually generated crop annotations. We used this like a sliding window strategy. I actually should point out this whole pipeline is actually available on GitHub under the name DeepaSlide, and it's very popular across the world. We actually created this GitHub and released it as open source tool, and every month actually we have hundreds of downloads and views. So if you are interested in this domain, you just definitely take a look at this GitHub repository. It's called DeepaSlide, and I think I put the link in one of the prior slides. So this task, as I mentioned, is actually much more subjective than actually polyps. So it was established the ground truths by hoping that all our pathologists would agree on one class was very difficult. So as a result, we decided to actually see the rate of agreement between 3 pathologists and our model as another rater or another basically annotator. So we had 3 pathologists in this domain. We call them pathologists 1, 2, 3 in our model. We also, so here you can see the kappa coefficients. So this is the agreement and also percentage of agreement for actually among different pathologists and our different pathologists in our model. And here you can see the kappa score for different classes. So if you actually look at this basically lines, you kind of can actually guess that our model is actually not any different from actually the agreement between our model and the pathologist is not any different from agreement between 2 real pathologists for this task. We also summarize these agreements between different pathologists and our model. We also use actually a baseline model that actually came out about 6 months before our publication. And we show that our model is actually tend to agree to the basically majority of the pathologists more often than our baseline model or any other pathologist. So this actually show that our model actually performance are basically on par. It can be treated as one like other pathologists in this domain with all of the nuances and variability in this domain. So here you can see the visualization of these results. So this is the sample, basically lung histology slides, and we asked the pathologist on the left to actually outline different types. So here color-coded, you can see different types of lung cancer pattern, and this is actually highlighted the regions that our model picked up according to our model picked up as the features associated with these classes. So I have another basic application that I'm going to talk about it more briefly because we almost actually half of my time is passed. So I want to go a little bit faster so I can talk about our methods in more depth. So this is basically is focused on the identification of celiac disease. So celiac disease, as you may know, is actually is prevalence is on the rise in the developed countries and in the United States. And actually, the gold standard way to diagnose that is actually through biopsy and actually visual examination of the biopsy tissue. So we actually we teamed up with Arif and his group to actually build a model to actually automate this task. So this is our data flow, and we collected actually more than 1,200 slides, and you can see actually the data is split among actually 3 different classes: normal celiac disease, and we have a class called duodenitis. This is actually like something between celiac disease and actually normal, and we actually have a different kind of implication for the patient. So we treat it as a separate class. So again, we have actually a sliding window methodology, and here you can see we actually got a pretty good accuracy, like in 90s range for the precision recall and the fundoscope. And I have the similar visualization, more detailed visualization, look at the different types of more focused and more high resolution part of the image that help the pathologist to actually confirm the results. And right now we are actually working, I think like maybe 4 or 5 different applications. These are usually type of like different type of tumors. We are looking at the bladder cancer tumor slice. We are looking at the renal tumors. We are looking at the brain tumors. So we are actually excited about helping pathologists in this domain, and the basically applications of this technology and how it can be actually used in real practice. But in the second part of this talk, I want to talk about basically some novel approaches that we have been working on, and how we are here at Dartmouth, we are trying to basically push the boundaries and build better methodologies in this domain. So as you may imagine, just like a sliding window strategy that worked pretty well and was reasonable in our applications has some major shortcomings. So one of them is actually require bounding box annotations, because this whole slides, sliding window, each time is actually looking at the small part of the image. So our model is actually need to be built and trained for actually analyzing a small part of the image. So the label should be associated with these like patches. So as a result, we need a pathologist to look at the actual whole slide and annotate the part or patches that actually are associated with every class that we are interested in. So that's the one major bottleneck. So annotation, as you can imagine, is time consuming, is actually resource incentive, and that's the major bottleneck in developing an application of this model. It would have been much nicer that we could actually, just rely on the whole slide label that you typically can extract from the pathology reports or in the tables or, in the structure format. So the other shortcoming is once we actually analyze every window separately, it doesn't really consider the correlation and the information that you can get from the surrounding window. And this is, as you can imagine, it's not a perfect situation. Context is very important. So we are actually we were not very happy about like just analyzing every window independently, and actually at the end we aggregate them based on the statistics of the confidence scores. And finally, this aggregation heuristic requires actually a lot of domain expertise and going back and forth and talking with the pathologist. So it's actually not very scalable process. So we wanted to have a data-driven approach that actually is scalable and can be learned directly from the data. So to solve this problem, we actually proposed the attention-based deep learning method to actually to analyze the whole slide. So our model, we actually overlay a grid on the whole slide and extract features from each grid. And our attention mechanism actually generates an attention map that actually assign a weight to each grid, and that actually weight identify the basically importance of the features from that grid for the actually final classification task of the whole slide. So we represent the whole slide based on the weighted averaging of these features and their attention map, the associated weight for every grid, and we have a holistic representation for whole slide that can be used for the whole slide classification. So here you can see that basically the schematic representation of this. So this is the overlay grid that I talked about. We basically apply our CNN. So this is the typical ResNet model for feature extraction. And we actually, here, we actually used multiple 3D convolution for generating this attention map. And we use that attention map to actually reweight our features from actually coming from CNN for basically representing the whole slide that goes to our final classification, for the classification test. So why is this model better? For multiple reasons. So the first of all, our model dynamically based on the actually content of the grid decides the region of interest, the important part for the whole slide classification, not based on those annotations that the pathologists actually put in during their annotation. It can be trained end to end, and actually it only relies on the labels on the whole slide, on the tissue level, not on the actually annotations that are coming from these surrounding bounding boxes for the regions of interest. And also, it doesn't require actually any heuristic and low-level, region of interest annotation. So it's actually much more scalable and applicable in different applications. And input size is flexible. So as long as you can basically, train this model on a GPU, you don't like those sliding window strategies. You don't need to basically be bounded to the input layer of your feature extractor. And so as a result, this is applicable to cases where training data is scarce and annotation are not available. So we tested this approach on the actually esophageal cancer classification. I'm not going to go into detail about basically this type of cancer, but basically here are different histological classes that we have in the progress of acid reflux all the way to actually esophageal adenocarcinoma. So we have Barrett esophagus and the low-grade dysplasia and high-grade dysplasia. And this progress actually happens only for 0.1% of cases each year. However, the important part is the mortality is very high for the cases that progress. So it's very important to actually identify these basically histological patterns to actually take action accordingly. So we actually work with our pathologist colleague at DHMC to collect around 400 slides. These slides are actually coming from endoscopy of the actually patients at DHMC in 2017 and 18. And we actually divided our data to development set, training set, and actually test set. And we also were interested to see how our approach is actually performed in comparison to actually our status quo approach, the sliding window approach. So for that purpose, we asked two experienced GI pathologists, Dr. Arif Srivanatha and Dr. Bing Ren, to actually annotate these region of interest just for the purpose of training our sliding window strategy. So this actually table summarizes our actually and compares the result of our sliding window approach to attention-based approach on 123 images. So this is basically each type of basically histology, and also this is the average basically accuracy, recall, and precision. You can see in almost in all the cases, we at least by 5 to 10%, we outperform the sliding window strategy. One important thing that I should again actually emphasizes this sliding window strategy is actually relied on detailed annotation that is really time consuming for pathologists to actually to perform. However, this attention model, it just relies on the whole slide annotations that actually you can easily get it from the pathology reports that actually come with their associated slides. So building these models are much easier because you don't need to actually with the pathologist to actually go through all the slide and annotate the region of interest. So it's much more efficient. So for basically demo and visualization purposes, we actually look at the attention map for adenocarcinoma class. And here you can see for this sample, basically slides from normal and buried esophagus with no dysplasia, how actually our attention model actually is working. So basically we normalize the attention map, so you can see it's kind of all over the place. This is because this attention map is actually sensitive to the features of adenocarcinoma that doesn't exist in these basically lower risk classes. So as a result, it's all over the place, and we can confidently actually classify the whole slide as actually, according to actually assign it to an associated type. However, in actually in the class of buried esophagus with dysplasia, adenocarcinoma, our attention map actually narrows to the regions that actually have those corresponding features. So the adenocarcinoma to the part that actually have adenocarcinoma features, and also in the cases with dysplasia, in the actually parts that actually this progression to cancer just started. So we actually verify these on many of these slides with Arif and his group, and we were very excited because we didn't really tell our model anything about the detailed regions of interest for these slides rather than the whole slide classes, but actually the model using the attention mechanism could narrow down to actually regions that were actually important for this classification. Now, in the last 5 to 10 minutes, I want to very quickly talk about another actually methodological advancement that we have been working in the recent years. So this is actually about building generative image translation model for data augmentation, and it actually is addressing one of the critical another critical bottleneck in this domain. For analyzing and for building these deep learning models, we actually usually need to access to actually large amount of data that's balanced across different classes. However, as you can imagine, getting access to this data and digitizing them is usually costly and it's not very easy. And also, the data that we get from different classes is actually driven by the prevalence of those actually classes. So it's very actually common that we don't have access to enough number of actually slides for certain rare classes. So our solution here is building an image translation model for generating synthetic and near real images for rare classes based on the actually images from common classes. So here we actually tested our model on the actually colorectal polyp images. So majority of actually these adenomous polyps actually are originated from normal chronic mucosa tissue. So we have plenty of actually normal slides that we can use actually to generate these actually synthetic polyp slides. We actually use CycleGAN. If you actually work in the domain of deep learning, you probably heard of generative adversarial networks. These are generative models that actually can use to basically generate new images, new actually data based on some prior or some other, based on some existing data. I'm going to talk about a little bit about our methodology in the next slides, and we actually have some filtering methodology to actually help our GAN, cycle GAN actually architecture to perform better for this specific task. And we used actually the actually generated images to augment the data, to basically add to the rare classes and train new models that actually that had improved performance. So this is actually the data distribution as you might remember from my my first application in this talk. And this is like across different type of polyps and also, normal. And you can see these like cysticerted adenoma or tubular villus and tubular adenomas. These are actually much the rare classes than like normal or hyperplastic. So about cycle GAN, by no means I can actually go in detail in few minutes about this, but basically it's as you might know, I really highly recommend if you're interested, just look at a few papers, especially this paper on cycle GAN on the internet, or I will be happy to actually stay after this talk and we actually discuss it. But basically, you can basically build a model that works on the source domain and actually on the target domain and translate the image from the actually source domain to the target domain. And these are very actually fancy images that actually come from this paper. I highly recommend looking at some of these images. You can actually have an image in winter and actually convert it to summer and some other fun applications to convert horses to zebras and vice versa. So what we did, we started actually with normal images, and we actually have the precancerous images. These are actually polyp images. We actually applied actually ResNet that was pre-trained on this actually precancerous images to actually find the images of polyps with high confidence based on our pre-trained ResNet model. And we actually use this rank filtering to actually only use the high confidence images as target images for our cycle GAN model. And we use this cycle GAN with normal images as a source domain and these high confidence polyp images as the target domain to synthesize precancerous images. We evaluate these synthesized precancerous images through basically data augmentation and incorporating it in building a classifier to see if indeed improve the classification task or not. And also we run a Turing test to actually see if actually our pathologists can differentiate these synthetic images from real images. So here I have a sample from our paper. So here you can see the normal image, and this is when we use all the target images to convert this actually normal image to TA tubular adenoma, tubular villus adenoma, and serrated adenoma. And this is when we actually only focus on the half of high confidence actually target images, 1/4 of high confidence target images, 1/8 and so on. So far. So you can see when we focus on only 32 of the target images with high confidence, we actually have had the best result. So in our Turing test, what we did, we actually asked 4 pathologists to look at 100 real images and 100 just fake or synthetic images, and they were blinded about like which is which, and we asked them to basically try to identify which one is fake and which one is actually is real. They actually didn't know how many fake images there are. We actually didn't tell them this is a balanced data set. They were blinded to all information. And our results show that all pathologists except one could not differentiate at least half of the synthetic images from the real images. And also our statistical analysis in these 200 images that were actually classified by 4 pathologists showed that at least half of the pathologists could not distinguish real and fake images at a statistically significant level. So I know I'm running out of time. So actually here you can see actually some images, figures from our paper that actually is going to be presented in NORP's conference. So we actually, here is the ground truth, fake and real, and this is how actually pathologists predicted in these images. This is where they successfully can identify real images, and this is when they actually they thought real images are fake, and how they actually some of the fake images they were identified correctly, but some of them they thought they're real. And this is actually, you can see the breakdown of their classification, by each pathologist and on average. Here, these are the actually generated images for tubular adenoma. We actually run the same Turing test for cystic adenoma, and you can see actually our results as well. And we were actually feel very good about, these synthetic images are very high quality. So we actually did a couple of experiments. The first one, we use only these synthetic images to build actually polyp classifier. And you can see, the cycle GAN. We actually not only use cycle GAN, which one of the GAN architectures that we could use. We look at a deep convolutional GAN, disco GAN. These are the other actually competitive GANs that we actually tried. And we saw that actually cycle GAN, the AUC is 0.68. So it is, respectable, but it's not as high as that we hope. But when we actually add the synthetic images to the real images, we actually saw that the cycle GAN images really improved the performance. The AUC only on real images on our test set, which was actually 261 hyperplastic images and 39 associated adenoma images. These are actually those two classes that I mentioned earlier, very tricky to differentiate. We actually saw that if we only use the real images, the area under the curve is 0.78. And we can improve that by 11 points. We add the synthetic images in the training process. And also, we had a little bit of fun with this GAN. So we actually first applied on the lung biopsy tissue, and we saw, wow, we can actually generate images that really look like polyp. And then we actually applied this on the dog images from ImageNet dataset. And I should say, this is absolutely our pathologist's favorite images. They really like these actually dog-like polyps. And I want to just add this is my final slide, and I will be happy to actually take questions. So this is all cool, and we are very excited about actually application of AI in this domain. But there are certainly several challenges that need to be addressed to actually moving forward. The first one is about establishing the reproducibility and generalizability of these models. We actually, as I mentioned, we are trying to actually run our models and verify that on a multi-institutional data set to show that this data works and performs well on the data coming from many different sources. We are also actually in the process of running prospective clinical trials to show that there's clinical value when these models are deployed in real clinical practice. Also, I should say that the other actually great challenge that needed to be addressed before this model be used is establishing the trust between the AI and clinicians and patients. So some of these actually, challenge can be addressed by actually building models that are explainable to pathologists. So there's this new, expression glass box AI in basically black box AI that actually lots of people are interested to build to actually address that. And also our clinicians and pathologists and patients need to be aware of and understand the limitations of these AI methodologies so they can interpret these models and use that actually in the informed fashion in real life. So at the end, I want to thank my group. So these are my students and researcher staff to really work hard in these projects, and this work was not possible without their hard work, and also our collaborators that have guided us through these projects, and also our funding sources from NLM and CI and COBRI that really was instrumental for this project. So at the end, I want to thank you for actually being here in this Friday homecoming afternoon. And I will be here and take your questions. Thank you so much.